good afternoon, everyone, and thank you for the opportunity to join this session today. It's absolutely fantastic to be here. So, as Rob said, my name's Noel Tomlinson, and within BMT, I look after the commercial maritime sector across UK and Europe. I've been with BMT for the last 8 years, and those of you who don't know us, we're a global multidisciplinary design and engineering consultancy with a core focus in the maritime sector. We've been designing vessels for the offshore wind sector for over 15 years now, and have over 50 wind farm support vessels in operation around the globe. I also have held a seat on the SMI Commercial Marine Group Council since 2019 and lead the SMI Workboat Working Group. I'm here this afternoon to talk to you about some of the challenges and some of the opportunities that exist when it comes to wind farm support vessels, and we'll echo some of the discussions that we've already had here this morning. What I'd like to start, however, by lifting up slightly and talking about the commercial small boat sector in general. Workboats, harbour vessels, ferries, and of course wind farm support vessels. These are typically day-running vessels, the majority under 50 metres in length, that operate around the extent of our coasts and harbours, forming an integral part of our maritime industry. I really strongly feel that this sector plays a really critical role in addressing some of the key wider maritime challenges of decarbonisation, autonomy, and digitalisation. And it's quickly becoming the proving ground for new innovative solutions and technologies that we're seeing coming through. When it comes to these vessel types, there's already a strong UK offering, including designers, shipyards, equipment manufacturers, service providers, and innovators, and it's fantastic to see a number of you here at the conference with us today. As I mentioned at the start, I sit on the SMI Commercial Marine Specialist Group, and in response to the increasing importance of this sector, we established a new working group in July last year, the Workboat and Coastal Vessel Working Group, or WWG for short, and I'm extremely proud to be part of that group. The group's mission is to provide a unified voice to facilitate growth and development within the UK supply chain for the design, build, and upgrade of workboats and coastal vessels. The working group is comprised of over 18 members, representing a wide cross-section of industry, from designers, builders, class societies, equipment manufacturers, and service providers. The group is working hard to identify and prioritise the challenges and opportunities currently facing the sector and where we can really add value. We're currently progressing with 12 initial work streams, which cover a wide range of topics, from engagement with the national shipbuilding strategy to finance and export, technical innovation, and sector promotion. Offshore wind represents a growth area and forms a significant and increasing proportion of this sector. So we heard from Stuart and David speak earlier about the sheer demand of renewables going forward, and I'd like to also explore the size of the prize. Now, there are lots of different statistics out there. We've heard different ones this morning. I'm sure we'll hear different ones going over the next 2 days. For the purposes of today, I'm going to use the recent DIT Offshore Wind Vessel Opportunities in UK and Europe report, which was published in November last year. So what did that tell us? Well, over the next 20 years, 87 additional crew transfer vessels were required for new developments in UK and Europe. Add in the requirement for replacement vessels for existing sites, and it's estimated to rise to over 250 vessels. Excuse me. 35 new service operation vessels, SOVs, will be required for new projects, the addition of replacement vessels increasing this close to 60. And on top of that, floating wind will possibly create a market for up to 20 new conventional tugs and multicats. So to summarise, a total of 330 new O&M vessels could be required for both fixed and floating wind by 2041. So more than one vessel every month for the next 20 years. Now, there are other studies out there which estimate the demand to be much higher, as we've already heard, but there is clearly a huge demand out there as we go forward. Today, approximately 15% of the 267 CTVs operating in European wind farms were built in the UK, with slightly more being designed. The challenge is, how do we increase that market share? Our home market, the demand for UK and Europe, is only part of the picture, though. As the world starts to adopt offshore wind as an integral part of the planet's energy production, many countries are starting out on their own journeys. one we started here in the UK over 20 years ago. These countries are looking to UK and Europe to provide the low-risk, high-performance solutions that only come from years of experience and knowledge of designing, building and operating these vessels. This presents a huge opportunity for us and sets us apart on the global stage. This opportunity, however, is finite. As with all knowledge transfers, the gap is continually closing. So how do we maintain that gap? How do we maintain our global status? Now, plotting a trajectory for the future often involves looking backwards at historical data first. So let's look at the journey so far. Wind farm support vessels have not always been the highly capable, complex vessels they are today. The early wind farm vessels were nothing more than small workboats and fishing boats. The requirement for dedicated designs, however, became quickly apparent, and some of the first CTVs to be developed were around 15 metres aluminium and GRP vessels. From around 2011, we saw vessel size start to increase, and due to the increasing multi-role requirements, these vessels were no longer just taxis for the technician's daily commute. They're now carrying essential spare parts and fuel for the generators within turbines themselves. The increasing size of the turbines themselves has led to the requirement for deck cargo to increase from approximately 30 metres squared to over 90 metres squared, and the deadweight capacity increased from 15 tonnes to over 50 tonnes, so more than a 300% increase. A post-2014 rule change that allowed over 12 technicians to be carried, with 24 now being the common standard, enabling more technicians to be deployed from a single vessel. Deploying more technicians to more turbines over a larger area, however, requires an increased range and increased service speed, both which require more fuel. Fuel capacity requirements increasing from 5,000 litres to over 45,000 litres. So we've seen vessel design evolve as the physical and operational environment that the vessels are operating in has also evolved. CTVs are now required to do a wide range of duties, which is why they're now often referred to as wind farm support vessels as opposed to crew transfer vessels. So let's have a look at what a modern wind farm support vessel really needs to do. First and foremost, they need to undertake turbine technicians' daily commute out to the farm in various sea conditions. This may be up to a 2-hour passage, depending on the farm and the conditions on the day. It's therefore important that these boats are fast, comfortable, and seaworthy. When out at the farm, they will transfer technicians to various turbine towers for the day's maintenance. By pushing up against the landing tubes, the turbine tower, they'll achieve a stable platform for the technicians to be able to step off the vessel and onto the turbine ladder. Wind farm support vessels are often required to transfer large spare parts out to the turbines for routine maintenance and breakdown. Operating out of the closest port or harbour to the wind farm will often mean that there's not the shoreside infrastructure. So this means the vessels need to be self-sufficient in terms of loading that cargo and require their own deck cranes. These vessels are also required to carry out other various duties, including fuel transfer to the generators located in the turbine towers and supporting the larger SOVs, as we've heard this morning, operating as daughter crafts to those larger vessels. Now, we know the maritime industry as a whole is tackling the rising challenge of cutting emissions and decarbonisation, as we're going to talk about a lot over these 2 days. And that's very much true for the offshore wind sector. So a modern wind farm support vessel also needs to be green. The real challenge is how do we achieve this without compromising on safety and/or performance? Acknowledging that the majority of alternatives to diesel have a much lower energy density, how do we balance the need for increasing performance capability, as we've seen over the years, with the need to reduce emissions? Now, what technical challenge do those requirements create for the designer? Well, I think at this point it's worth stating that vessel design is not a single-step process. There's a number of key considerations with complex interdependencies and lots of trade-offs. We have, as an industry, learned over the years what works and what doesn't, and the vessels are continuing to be optimised. With the evolving requirements, technology advancements, and new operational environments, however, we need to keep challenging ourselves on what that solution looks like. Now, the hull form is a crucial part of any new vessel. With varying currents, wind, swell, tide, experienced at the towers themselves, it's vital that these vessels are highly manoeuvrable. And one of the reasons why catamarans are predominant hull form is due to their wide set-apart rudders or propulsors. As I mentioned, the vessels need to be high-performing and comfortable to get those 24 technicians out to the turbine towers to start their day's work, making seakeeping and stability crucially important. Having designed a variety of hull forms, from conventional catamarans to semi-swath and swath, In 2012, BMT developed an extreme semi-swath, or XXX hull form, specifically designed to improve seakeeping and ride quality for this application. The careful choice of hull form with the addition of active rider control systems utilising interceptors, trim tabs or stabilisers can provide significant motion reduction and reduce fuel consumption. Another technical challenge is safely performing the transfer of the technicians itself. The vessel only sticks to the landing by friction against the bow fendering. Now, good transfer performance is achieved through a combination of a well-designed hull form, high level of bollard push, so approximately 15 tonnes, and a high-performing fender system. This is another area where BMT have invested a lot of time to develop our innovative active fender system, or AFS. Now, as the vessels are getting larger and the installed power increases, being able to reduce impact loadings for the landing and the vessel and the personnel is highly, highly important. The AFS articulates and absorbs shock, allowing the captain to engage with the landing tubes with more confidence, reducing risk of damage, injury, and increasing the whole safety of the transfer operation itself. The maneuverability, speed, and bollard push requirements mean that generating power and then efficiently transferring it into the water is equally important, with power and propulsion configuration and selection critical to an effective design. But as we have seen, these operational requirements are not fixed and they're continuing to evolve, along with the technology and the solutions we have in place to address them. So with both the maritime and the new renewable energy sectors going through significant periods of change and advancement, how do we future-proof designs? Offshore wind is growing considerably all over the world, and many countries declaring extremely ambitious installed capacity targets for the years to come. The size of the wind farms, the distance offshore, and the turbine size are all increasing rapidly. And we also begin to see the introduction of floating wind, which brings with it a number of new challenges and opportunities, both with the installation and operation and maintenance phases. We are decarbonising our maritime industry with tightening emission regulations, the introduction of alternative fuels, and increasing digitalisation. These are all works in progress, however. We don't have all the answers yet, and the solutions we do have are continuing to be advanced and replaced at speed. So how do we design an asset with a service life of over 20 years to cope with this rate of change? We don't know what the world will realistically be in 10, 20 years. Unfortunately, we don't have a crystal ball. But we do know it will be different. And that, for me, is the key element. Change and advancement is inevitable. What we can do is plan for that change. And one of the main components of decarbonisation is moving away from diesel and carbon-based fuels, as we know, and that requires different power and propulsion systems. Although there are a couple of test cases around the world, the production, supply, and infrastructure for the majority of alternative fuels are not yet mature enough to make it a commercially viable option today. Batteries provide a good solution, but due to the challenging operational profile of a wind farm support vessel and the current maturity of battery technology with regard to power density, an all-electric vessel is also currently not often a commercially viable option today. So where does that leave us? Well, in a lot of cases, it dictates that vessels being designed and built today will in fact have diesel engines. So does that mean we aren't advancing? Far from it. The shift to hybrid and diesel-electric propulsion opposed to more traditional direct drive main engines offers a lot of benefits. Essentially, the power and propulsion system is now electric. The current production of that electricity on board is via a diesel prime mover, but this doesn't always have to be the case. Replacing the diesel generators with another form of energy generation in the future can be made fairly easy. The rest of the power and production system remains untouched and is installed for the life of the vessel. The shift to diesel generators also means that there's no longer a need for them to be close to the propulsor in the engine room, which opens up new layout options. The shift to hybrid system also means that batteries can be utilised, and although not to be able to be the sole power source, they provide a number of really beneficial functions. From peak shaving, reducing the size of the generators required on board, to providing an emission-free harbour mode or enabling a zero-emission loiter mode out at sea while the vessels are waiting to retrieve technicians. We've established that the power source and the associated fuel will be updated, but we are not sure at this point what it will be replaced with. So what other considerations can be made? Well, one of the main ones is space provision. Normally on every vessel, every inch is utilised, as we know. But if we're going to be installing new technology, anticipating new technology, then let's leave space to fit it. Where can we fit 4 but not with. And I know from people in the defence industry, that's a common term, but now how do we bring that into the commercial world? Fuel cells, batteries require additional ventilation, monitoring, fire suppression. These can all be anticipated in the early build. One of the main challenges with alternative fuels is that they're not as power dense as carbon-based fuels, so one of the biggest drivers is the powering requirement for the vessel itself. The more fuel efficient the vessel can be, the more likely that an alternative fuel can be a viable option. From hull form design efficiencies to the use of energy-saving technologies, whether that's hydrodynamic appendages, paints, waste heat recovery, even wind-based technologies, all should be considered within the design phase. The last point I'd like to cover is operational profile analysis. A vessel is designed around a number of key requirements, two of which are influential when it comes to alternative fuels, and that's speed or range and endurance. How fast does it need to go and for how long? They dictate not only the hull design, but also the engine selection and fuel provision required on board. Now, operators naturally want to specify and invest in the most capable asset they can, but so often vessels spend their life operating outside of that original design envelope. Accurately modelling and analysing the vessel's operational profile can optimise the vessel's operating requirements and really enable the accurate modelling of battery charging, schedules, and modes of operation that can really enable some of these technologies. With understanding the true requirements of the vessel, some early design considerations, and knowledge of both the technology and upcoming regulations, I believe we really can design for both today's realities and tomorrow's challenges. So there's clearly an opportunity. It's a growing market, and the UK supply chain has pedigree. Yes, there are technical challenges, but we know what they are, and we're working towards them. So how do we do better? How do we as an industry respond? Well, we need to position the UK as a green maritime leader in offshore wind, and to do this, we need to unite as an industry. We've heard this already this morning, the collaboration word. From designers, shipyards, equipment manufacturers, service providers, to regulators, academia and government. We talked about home markets. This is our proving ground. This can give industry the confidence to invest. We need to facilitate UK content in future UK offshore wind developments. Knowledge is power. We need to encourage early engagement and collaboration across the enterprise, from the wind farm developers through to the technicians themselves and everyone in between. The vessels need to interact with the turbines. They need to transport spare parts for the turbines. Their operating profile is dictated by the turbine maintenance schedule itself. We need to adopt a system of systems approach and not design in isolation, informing the requirement rather than responding to it. As we've seen in the automotive industry, taking an existing car model and adding batteries only goes so far. We need to adopt the Tesla approach. When it comes to power and propulsion systems, we need to design around the system, and that requires collaborative R&D across the supply chain. As we've discussed, we need to incorporate flexibility and adaptability into our design. The more we understand about new technologies, the rate of development, and the future trajectory, the more we can anticipate tomorrow's challenges into the design of today. And the last thing I would like to mention is diversification. Now, out of 66 construction vessels currently in operation in Europe, none were built in the UK. We have a strong pedigree in wind farm support vessels. How can we build upon that wider knowledge and experience and the opportunity of floating wind to enter the construction vessel market within the UK? Many challenges, but importantly also many opportunities. Supporting a critical, innovative and growing sector, I believe wind farm support vessels have a key role to play in the future of maritime, in the future of global energy production and the future of the UK. Thank you very much.